And okay, recording has started. All right, so today we're gonna actually like carry on with Q as an abstract data type, and then we'll talk about like some of its applications, or one of its use case, or some of its use cases. And then we will discuss the algorithmic analysis, how you can analyze algorithms, which is a very, very, very important topic. And the reason behind why actually we followed like the stack and the queue as a data structure, so we got the listing and stuff. But then we wanted actually to discuss the algorithm analysis right after that. It's because because there are so many things that we need to, for example, you need to choose which data structure you would like to do, to use, I mean, or which algorithm you would like to do. And based on these choices, actually, I mean, these choices which we have to do are basically, they are based on this idea of how you can analyze an algorithm, or why you're going to pick up something even though it has some sort of drawbacks, right? So yeah, so let's actually get along with queues first. So a queue, well, actually it glitched on me right away. So a queue is exactly like a stack. So let me just put this there. So it's like the stacks, or like let's do it like stacks. Queues are list. Oh. Query on lists with a protocol or a constraint. Okay, where insertion is done from one end or at one end, and deletion is done or performed at the other end. This is as simple as it can get. Okay. So practically speaking, when you're actually discussing queues are actually like, so the first guy who comes in, or the first element which comes in, is the first element which goes out, practically speaking, right? So this is this is what we like. This is unlike actually stacks, which is like the last in is going to be the first out. So let's actually like put this down in a very simple yellow color here. So queues are a first in, first out, aka FIFO, ADT, abstract data type. Okay, this is their policy. Stacks are going to be lethal, so last in, first out. Okay, A stack has, a queue has the following operations. So queues, if you would like to define a queue, and you can say it is a queue, it has to support these following operations. The first one is going to be, let's choose another color here, which is going to be in queue. This is your insertion. Okay. 2, we're going to have DQ, which is your deletion. In fact, this is like return the next element, which is going to be like the first one which got in. So the next element, and remove it from the list. Okay, so this is basically it. Okay, then you have peak, which is get the next element without removing. From the list. Okay. Then you have check if empty, and this is like the same as the stack. So check if empty. And it just simply checks if the queue is empty or not. Okay. Usually people say that the insertion happens from the rear end of the stack, like from the and the removal is happening from the front side of the stack. So or sorry, the queue. Sorry. So let's say let's have an example. Okay. So let's say that you have an array. And the actual implementation honestly doesn't matter, right? So it's really up to you how you're gonna implement this. But usually we, like, at least in books, we usually say, okay, this is how we're gonna actually do the insertions, and this is how you're gonna do the removal or deletion or dequeuing, and the rest is like you figure out the rest. Okay, so that's basically it. So let's say you would like to enqueue something. So let's say you enqueue 10. And 10, what's going to happen is it's going to be inserted from here, so it will appear right here. If you would like to enqueue 9, your queue will actually look like this. So you're going to have your queue will look like this. 10, because you are inserting from here. Okay, and then 9. Then if you would like to enqueue 8, your queue is going to look like this, obviously, which is 10, 9, 8, because you got it from here, right? And then you would like to dequeue. Right now you're dequeuing operation, so just simply dequeue. And what's going to happen is you're going to be just simply removing the next element. So this guy is going to pop out. So you're going to actually get 10 at the end, and it will be left in the list with 9 and 8. So this is basically what a queue is about. There's nothing difficult or fancy about it. It's like it's almost the same as the stacks. It just except it just has a this specific policy. Okay, and stacks. I mean, and queues in general, they have interesting use cases, by the way. So if you would like to, so let's actually like discuss these use cases because we see them and we use them almost every day. For example, let's put this under a nice blue color. Use cases. So what are the use cases? For example, organize a shared resource or shared resources. Would you like to organize memory, or you would like to organize task execution? So resource, or let's put it that way, task execution. For example, such as printing jobs. If you have a network printer, okay, and there are multiple people on the same network, unless if somebody is printing like 10 pages and somebody else is printing like 5 pages, unless you don't want the papers to be mixed, like one page from one person and another page from another person, or 2 pages and then 1 page from different computers, what the printer does is like, or yeah, actually the printer does is it does like this queue bit. So once it receives the request or multiple requests, it puts them on a queue and just executes them one by one. The first person who got in, the first person is going to be served. So first served, first come, first served. This what we that's what we usually say. And the printer will just simply start to like pop out the papers like in that specific order, which actually the task has just got received. So that's one way. So for example, like printing jobs, you can actually also use it for you can use it for organizing process executions. If I remember how to write. Okay. Organizing process executions, and this is what your operating system always does. In fact, your operating system has some sort of a priority queue to its like execution planning bit. So for example, like there are some processes have higher priority than the others, and so on. By the way, priority queues are going to be discussed later on when we visit, I think, trees, because they share a lot of characteristics with trees. Actually, we're going to talk about the heap later on. So yeah. So yeah, this is like one of the applications, organizing as well the processes execution, which is similar to the printer, as well as, for example, customer support calls, if you want to. Wow, I cannot. Today everything is glitchy for some reason. Okay, customer support calls. One of the interesting applications which you can do is actually having a circular queue, a queue that never ends, which you can think of it like a messages on a billboard. just simply keep rotating and rotating and rotating. So this is one of the interesting bit. However, you're gonna be keeping track of, like, let's say 2 pointers, and you make sure that you don't run out of elements. So for example, if you dequeue an element and enqueue an element, you need to make sure that you don't run into dequeuing an empty element, right? So if you look at so let me write this down and let me give you a short example here. So circular queues, which you can actually implement, by the way, circular queues for rotating messages, for example. So for instance, let's say you have a billboard, okay, and then you have one message appears, then it disappears, then it gets another message, then disappears, then the next message, and so on and so forth. You could have some sort of like a circular queue. And obviously, I mean, when you dequeue, you're gonna actually like remove an element, but for the sake of the argument, we're gonna dequeue and remove an element. But right now, I mean, you usually don't, you shouldn't, in this case, at least remove an element. You're gonna be peeking the next element all the time. But let's say you enqueue message A, then enqueue message B, then enqueue message C, then you dequeue message A, right? It will be just, sorry, when you dequeue, message A will come out. Then you enqueue message D. Then when you dequeue again, the message B will come out. You enqueue message C, right? And then when you dequeue again, hang on, this is E, should be E, sorry. Then message C goes out, and then you enqueue again A, B, C, D, E, F, and then G, for example, you enqueue, and then you dequeue, and then you dequeue, and then when you say A, B, C, G, H, when you would like to enqueue right now, H will happen to be here instead of A because this has been empty, right? So you can actually use this like kind of circular queue. You're all the time, you're never running out of space. You're just simply keeping inserting and dequeuing stuff. I mean, eventually, if you enqueue more than what you have, definitely you run out of space. But if you are actually keeping enqueuing and dequeuing, and there's always a space where you're going to actually insert something, then you're going to actually you're going to have this interesting circular queue happening. Sometimes actually in some devices, if you are actually organizing resources and stuff like that, in some cases, sometimes you actually run out of, just it says that the queue is full, and it tells you to wait until the queue is empty so it can actually accept more tasks in some of the devices, right? Okay, so this is regarding the queues. There's nothing, I cannot think of anything that is important to say about them. That I mean, there are important data structures and everything, but they are super simple. So if you guys have any questions, feel free to shoot before I move on. No questions?
No questions.
No. Okay. Oh, actually, I have a ruler. I could use it actually, like just draw on a big line and take it out. All right. Yeah, okay, I will actually like do it here. Okay, let's talk about one of the most important topics in algorithms, which is the algorithm analysis. This is super, super important. You're going to have questions about these in your exams. This is 100%. You're going to get an algorithm that you need to analyze. You're going to get code, and then you have to say what is the time complexity and the space complexity and so on and so forth. We're going to discuss all that, and we're going to take it slow. So you guys, if you have any questions or anything, just simply like shoot. The main thing is that you guys understand, you fully understand what you are doing, because I've seen on tests people are just simply answering random stuff. They just simply like randomly put a annotation for no reason. Some get it right, some get it wrong. You feel like in some answers, like it really feels super random. Like the people just didn't actually look what they were doing. So in order to save you from this kind of crazy way of solving your problems, we will take it even slower this time than the last semester. Let's talk first of all, before we're going to dive into algorithm analysis, but we need first to define what an algorithm is. Okay. Let me, what do you constitute under an algorithm, right? So let's talk about the characteristics. Come on. Was it I cannot remember honestly. Characteristics of algorithms. The word algorithm came from the guy's name from the 900 so 900 900th, I think, the year from the guy is named Al-Khwarizmi. He actually originally from Uzbekistan, and he was actually a head of the science department, I think, in the back then when the Islamic Empire was I think in Iraq or in Iran it was situated, and he was and he is one he's actually the one who put the science of solving the problems step by step. He actually one of his interesting books were about the Hindu arithmetics, which apparently got lost and then resurfaced back again as a translation sometime, like I think 200 or 300 years later. I think it would be an interesting. I think it's interesting for you to read a little bit of the history about the guy, since he actually the one who like described how problems should be solved, how you should tackle problems. I mean, in terms of the way of thinking about them, right? So when you look at what you constitute as an algorithm, right? Before anything else, because anybody can come to you and then they say, hey, here's a piece of code, this is an algorithm, right? And any piece of code can be an algorithm, right? When some people can think of it that way, and actually it shouldn't, right? This is the most important bit. When somebody says like, this is an algorithm, you can say yes or no, because algorithms usually they have a specific definitions, like specific things that characterizes them. Okay. So let's talk about their characteristics now. Let me have this white. Okay. Here. So an algorithm can take zero or more inputs. Right? So it can actually like either take an input or at least like okay, it can take no inputs at all, and can take some inputs, right? So an algorithm that doesn't take any inputs is like, which I think it's a little bit of a bit misleading. But let's say that you can think of it as the generative algorithms, like Minecraft, for example. When you generate a world, you just don't give any inputs; it just generates it. Now, of course, there are predefined conditions that has been set as an input from within the function in order to generate the world. But when you call this generation, this procedural generation bit, you actually just generate the whole world without any user input. I've received an email recently, with an argument that in Minecraft you can actually put the randomness, you can put the seed, you put a certain number in there for the generation, and this is actually a valid point. Minecraft is, if Minecraft didn't offer this seed you can input, it actually like satisfies this idea of an algorithm that takes 0 inputs. The seed which you put in Minecraft is actually ensuring that you get the same world every single time. So let's say if your seed is like 1, 2, 3, 4, 5, for instance, and you liked what the algorithm has generated based on that seed, right? And you would like to share this. So what you can do is just simply give that number to a friend, and they input that seed, and they will immediately get exactly the same world as you have, including the resources, including everything, right? So Minecraft creators, for all the intents and purposes, they could have just simply all the time created random seeds every single time, just not to have the same world ever, let's say so, or with a very, very much less probability. Let's think of this that way. Algorithms that takes more inputs, let's say like the searching algorithms or sorting algorithms and such, okay, and which we're going to discuss probably later. So hopefully this one makes sense. Let's move on. The algorithm must generate at least one output. And this is very important because you cannot call an algorithm as something that solves a specific problem, and it just simply doesn't give you an output, right? You cannot have an algorithm that's simply just like a black hole that takes in stuff and doesn't spit out at you anything. Well, okay, black holes emit the Hawking radiations and other that stuff, but anyway, like it should actually give you something back, right? As an output. One of the things which algorithms also is characterized by is definiteness. Which means it should give a tangible answer or a realistic answer. Which is again super important. If you cannot have an algorithm that gives you like impossible answers to questions that cannot have, impossible answers to questions that doesn't have such answers, like what could be like the impossible things that could happen, like what? No, well, it really depends on the applications right now. For example, in some applications, let's say in some applications, square root of -1 in some applications, let's say, is not a good answer. It's an impossible answer for the given problem, right? So an algorithm should always give you like something that is like a tangible answer that it can be actually useful or used. Okay. Finiteness, again, depend on the application. You shouldn't have, but this one actually makes sense, I think. You shouldn't have an algorithm that infinitely loops without an output. Okay? So that's, which makes sense, right? If you have an algorithm that's just simply like loops infinitely and doesn't give you an output, it's just a program that's got stuck. And it has to finish something to give an output for you. If you have games that are procedurally generating the world as you go, this is actually some sort of an output, even though it's a while true statement, while you are actually in the game, it just simply keeps spitting out world elements. This is also fine. It's actually finite because there is an actual tangible output, right? But it cannot actually take in and like you cannot actually run the software and just doesn't give you an output and you call this an algorithm. It is not. All right. Effectiveness. So it has to be effective. Wow. Hang on. Effective. Okay, there we go. Again, actually the tablet usually doesn't, like the tablet mode, it doesn't glitch. It's just because when we're recording from Microsoft Teams, when I record the screen, somehow it starts to glitch all over the place. So apparently Microsoft needs to work on this. It has to be effective such that it can be useful or used, right? So imagine that you would like to calculate or to have an algorithm that calculates, for example, a missile trajectory. If the algorithm is super slow that it actually can give you an output in like 1 hour and the missile is approaching in 5 minutes, it's actually kind of crazy useless, right? So effectiveness is one of the main elements or main characteristics of an algorithm. Of course, there are some algorithms which cannot be more effective than what they are because this is the nature of the beast, the nature of the task, which has to be executed. But if you want to call an algorithm, it has to be effective in the field where it's actually trying to solve the problem, or in the problem space which it's trying to solve. Okay. So these are the characteristics of an algorithm. This is what defines what an algorithm is. If an algorithm satisfies these points, or if a problem solution satisfies these points, then probably we can call it an algorithm, right? Hopefully I didn't miss any specific points. Now, now that's out of the way in terms of definition. I would like to talk about the analysis bit. So since we know what an algorithm is, let's talk about the analysis of the algorithm. So algorithm analysis. Okay. And we do, whoop, we do analyze an algorithm according to the following. One is time. How much time does it take, or will it take, to execute, which is super important. If you are having a, if you look at Google search is actually searching through huge catalog of websites. It's like, I don't know if it is in the billions right now, right? And when you do a Google search, you immediately get a result almost like in the fraction of a second, right? And this is because their algorithms is super effective. That their time, that the time execution is that tiny. Okay, so if Google search took, I don't know, like 1 hour or 2 hours in order to search on all those billions of websites, then probably it wouldn't been that effective that we can actually like viable to use. So that's why we always analyze algorithms against, we analyze the time execution of an algorithm, right? Another one is the space. How much space, how much memory space it will consume. Because sometimes some algorithms, they're actually quite memory intensive. So when they actually get, when you would like to search or sort, they allocate more memory in order to search or sort. Are you actually going to allocate double the memory or triple the memory just in order to make your sort effective? So maybe you're sorting or you're searching, it can be super fast, but you are consuming a huge amount of memory because you had to organize your data structure in a way that you wasted that amount of memory, right? So, or used it, let's say, not wasted it. So use that amount of memory just to make your algorithm effective. So maybe it will run fast, but it will take huge space, or maybe it will run slower, but it takes much less space. So you have these things that are happening, and we're going to explore this in the subject. So we're going to see this in the subject. Network. Wow. Hopefully, I remember how to write. So network bandwidth. How much or how many times you're going to do network transfer? So how much what would I like this? How much data to be transferred? Oh boy. Okay. I think it's 1 R. Okay. Transferred. How much? How many megabytes are going to transfer over network? And I'm talking about this because let's say that you are trying to resolve. Let's say that you would like to actually do a huge calculations on data, but the data is super huge that you need to cut them down in chunks and then send them over a network, right? And then let the nodes or let the small computers, let the other computers on the network do pieces of the job, right? Now you're gonna actually have to transfer data, and right now it will be, the question will be asked is like, how much bandwidth are you gonna consume in order for you just to do your calculations or execute your algorithm, right? So this is one of the concepts regarding the like how do you analyze an algorithm? You can analyze the algorithm, let's say network bandwidth, beside the space and the time. How about the power consumption? If you are making an embedded system, will it actually, how much use it will use from the power budget? How much will it consume? How much power will it consume from power budget? Right. Remember that when you are actually working with embedded systems or working with any devices that they have these systems on chip or something similar to your phones, let's say, usually they have something which is called a power budget, where they allocate certain amount of power to certain chips just to make sure that it actually like doesn't consume a huge amount of battery for nothing, right? So that's an important bit to mention here. If you look at Bitcoin mining these days, at least by the time of this recording, if you would like to do mining, the algorithm is so heavy that it requires really like a very high CPU cycles. It actually consumes a lot of power, right? So the power consumption is right now also like is a question on the table. Is this algorithm viable? Can we make more efficient algorithm that doesn't consume more power, for example? So that's that. Let's say if you are doing something really low level as well, which you can actually think of it in a lot of computer graphics applications, depending on what you do, or for example, if you were one of those, if you are one of those people who are working on NES games or old Sega games, they had to think about CPU registers. And right now we do think about CPU registers in some cases. So how oh, okay, how just the thing glitches. How many CPU registers you are using? The thing is crazy. Oh. How many CPU registers you are using? Or are you actually for the algorithm? Let's say so. Okay. And this is, for example, like if you are making an embedded system or something like that, using, for example, Arduino or anything that is a little bit lower or lower power, or it's not that powerful. You can actually like monitor right now how many registers are you using, because you are trying to be as efficient as possible, so you don't run out of registers because of your algorithms, for instance. Okay. Just to be clear here, and this is something that a lot of people make a mistake about, and then we will take a break. And I will actually write it in a different color just to make it stand out. Algorithmic analysis are mostly approximations. okay, which doesn't completely, whoa, replace profiling. Profiling is usually the act of monitoring the system or monitoring system when it executes the software. You can actually measure the time it takes, measure the space it takes, so you can be 100% sure how much resources and how much time a certain thing or certain software actually runs. So algorithmic analysis is just, let's say, it tells you, does it pay off to do this? Let's say. And if it pays off to do this, right now you profile, right? So right now you implement and then you profile. We will talk about it even further after the break. So we're gonna dive deep after the break into how we do algorithm analysis, and we're gonna take it slow, step by step. So hopefully it's gonna be smooth. Any questions so far?
No, everything is clear.
Okay. All right. I will let you. I will actually give you a small break, and then after the break we're gonna continue. So see you after the break.
How long the break?
10 minutes.
Right.
So 11 and 15. All right, can you hear me?
Yes.
We can.
Yes, we can.
Perfect, perfect. Now let's talk about the time and space analysis. Let me just draw a line here, and I'll use this actually. So let's talk about time and space analysis, which is actually what we're going to be concerned with throughout the semester for now. We are not going to talk about the the network consumption or the registers, because for all intents and purposes and the scope of this course is we don't need that. We actually like not we don't need them, but just we are not gonna explore them for now. So let's talk about a simple program. First of all, just to be clear here, when writing an algorithm, depending on the book, actually even, we usually use a C style language. Okay, so if we would like to write an algorithm, we just simply use a C style language. Sometimes we change how we are writing the syntax, but we are not actually bound to a specific syntax, right? So before actually carrying on, let me give you two types of analysis here, because this will describe a lot of things. So if you have something which is called a priori analysis. And then we have something which is called posteriori analysis. For testing or analysis. Actually, it's more akin to testing rather than analysis, because you're already really testing this. So in priori analysis, what you are testing or what you are analyzing usually is an algorithm. And an algorithm is just something you write on a paper in a C-style language. Okay. It is usually, as you already could tell, it is independent or language independent. So we don't care what kind of a language it is. Is it going to be written in Python, C#, JavaScript, whatever? Language independent. Okay. 3, hardware independent. Okay. 4, we measure the space or time and space functions. Okay, and these are just you are measuring them in certain units. For example, the space, you're measuring them in words, and time, you're measuring them in units of time. 1 unit, 2 units, 3 units. Because so for example, let me be precise here. So a word is I think a word is 8. Was it 8 or 16 bytes? I really forgot right now. It's actually used in, like, if you look in the old books, you'll see that people are actually talking about, they don't say the measurement in bytes or bits, they measure it in words, because different back then, long time ago, different computer architectures existed, and their single and the smallest bit of memory, like the smallest unit of memory was actually different. For some computers, they were 16 bytes. For other computers, they were 8 bytes, for example. Excuse me. So we could have we could actually have a computer with different different sizes, like different the smallest amount of information size. So that's why we call this the word. We say, what is the word in that architecture or in that computer? And it will tell you the word is that X size, for example, right? This is when it comes to space functions. In posterior analysis, it is actually right now you are not testing an algorithm anymore, you are testing a program. So here you are you are analyzing a program. Program. 2, you are actually language dependent, because right now it really depends on the implementation. You're gonna get actually interesting results. In some languages, you can get some certain algorithms running faster than the others because of the specific way of how the language actually gets compiled. So you're going to be language dependent. You're going to be hardware dependent, because you want to know what are you testing this on, or what you are running this algorithm on. Are you going to run it on a Raspberry Pi or Arduino? Are you going to run it on a phone? Are you going to run it on a budget phone? Are you going to run it on a PC? Are you going to run it on a mainframe? So you are hardware dependent here. Dependent. Okay, and 4, your time and space are actually measured in milliseconds or microseconds or seconds. So this is units, and this is words or a word. This is going to be seconds and microseconds, and space, which is going to be in bytes, megabytes or gigabytes or whatever, right? So you get the idea. So you are actually like literally measuring things in its own like measurement unit. Okay. Now this is out of the way, so we understand like what is the difference between a prior analysis and a posterior analysis. Let's take an actual example. All right. Depending on the book, one of the books which I've given you, I will show you its syntax actually. So let's say that you have, and let's say that you would like to have an algorithm that, and its job is just to swap 2 numbers. Okay, so swap A and B. So let's say you have, I'll actually write it here, or, I mean, you can, okay, let me write it here. So you have several variations of this. So you have swap, and then a function that takes A and B. Some books, they actually express it that way. So you make a temp equals to A, then A equals to B, then B equals to temp, end of the program, or end of the function. Now, if you can see here, you haven't defined any data types. Nobody cares about the data type. For all the intents and purposes, you just simply defined how you can swap 2 variables, how you can swap A and B. If A and B happens to be a person object, then let it be person object. You're swapping 2 persons. If A and B happens to be integers, they're going to be integers. Floats, they're going to be floats. And they will work all the time the same, because it just simply describes how you can actually swap them. There might be additional code or implementation specific detail related to a language. For example, in C# or in JavaScript or whatever, or Python, it really depends. You might be, for example, needing additional lines of code to make sure that the references are keeping their integrities and so on and so forth, let's say, for example. And maybe this algorithm will grow in terms of lines, but basically speaking, this algorithm describes how you can just simply swap two objects. And this is why there are no data types anymore, right? It just depends on what you would like to use it for. Now, you might actually get it in books like this, or you could actually have it the same like in in Pascal, let's say. So you can have something like begin, and you can see it actually in books. Temp equals to A equals to B, and then B equals to temp. And the reason why, and then you have end. And the reason why you have these two column and then equals, column equals is an assignment operator. Sometimes in some cases, because in Pascal there's a difference between assignment and equality, and they actually trying to stress that out, or to stress that out, like emphasize it, okay? So that's why you have this colon equal, and you have as well equals in Pascal. So so this is one way of doing this. Another example, which you're going to see actually in the book, which I've actually given you, Introduction to Algorithms by Thomas Corman and the rest. They have actually something along these lines. So you can have actually swap, and they do some indentations, right? So they have like temp, and then arrow A, and then A, arrow B. So assign B to A. This is how it's being read. And then assign temp to B. Okay? This is one of the ways of, there's also another way that people actually write algorithms, right? So this what you have seen so far, all of this is called a pseudocode. This is called a pseudo. Oh. I don't know why the pen is glitching on me right now. There you go. All of this is in fact a pseudocode. So this, and this. Okay? These are pseudocodes. Pseudocodes because they are not a compilable. You cannot compile this, right? So that's that. Okay? So let's do, how do we actually do algorithm analysis? How can we analyze an algorithm, right? That's the interesting question here. So let us actually put this in. How do we analyze an algorithm? Erase everything, okay. Algorithm. Ooh, sorry. It's amazing how it glitches actually. Okay, there we go. How actually do we analyze an algorithm? So if we take the swap example, so let's actually take it right now. And let's say we are actually swapping A and B. And then I will actually write it in C style. So we have a temp A, temp equals, sorry, to A. And then A equals to B. And then B equals to temp. And then we are done. Okay? So let's do here time analysis. So let me just put let's put a barrier somewhere right here, like so. And this is going to be our, let me choose one. It's going to be here, time analysis. Okay. So how can we analyze this? Now, the first thing is when we do an assignment, when we do simple statements like these, like the assignments, when we say A equals to B or A equals to 10 or X equals to 500, doesn't matter. This assignment operation usually takes 1 unit of time because it takes 1 CPU cycle to execute. Now, it really depends on how large is the data, right? Assignment can actually take some time or can take much less time. It depends on how much data transfer is going to happen, right? It can take half an hour, depending on what you do. I mean, obviously it shouldn't, but I'm just saying it here for an example. So that's why in algorithmic analysis, when it comes to analysis, we usually do approximation, and when we actually analyze the algorithm, as I say in the priority analysis, we measure the time in units, right? So we say that this will take 1 unit of time, right? So it just takes one CPU cycle, let's say, or whatever, right? So it takes 1 unit of time to do this operation. A equals to B is as well would take 1 unit of time. And B equals to 10, this will take 1 unit of time. Okay? So at the end of the day, the function of execution, like how much the function of time for n inputs. So you call this time, we call this function n number of times. So that's why we call it the f of n, function of n, right? It's going to equal to 1 plus 1 plus 1, which is going to be 3, right? So this actually takes 3 time units. And whenever you have a specific number like this, we call this a constant time. It takes a constant time to execute. So we know it's whether it's going to be a person or an integer or a faculty. If you're swapping two objects of the same type, then you're going to actually have a constant time of 3 time units, and this is it. Is it going to be 3 seconds? Is it going to be 3 milliseconds or microseconds? It really, it's right now really doesn't matter. Right now we know it takes just exactly the time at 3 time units. Okay. And by the way, we say that this is actually like, it's actually 1 because there are no nested statements. And I will actually give you in a minute a quick example here. So let's say that you have something like this. Example, which takes A, B, and C. And then you have, I don't know, A equals to 10. Then you have a function which takes A times B, or let it be that it's just a function that takes A. And then, for example, B equals to C, and C times 10, whatever, right? So can somebody help me out here? So this is going to take how much?
1 unit.
1. How much does this guy take?
Well, we need to go into the function and see what it's going to do.
Exactly. And this is the trick here. If I actually don't describe this, this is going to be unknown to me, right? And this is why we say we're going to assign 1 time unit for something that is not a nested statement. This means that I need to jump outside, analyze it, then get back, right? Because this can be actually n-cubed for all what I know. You never know, right? And this will take obviously 1, and this will obviously take 1, right? Because it's just a simple statement, not a nested statement, right? So this is a very, very important point I would like to bring up here. So you need to be careful about this. There are always trick questions in the exams, you know. Okay, so let's talk about the space analysis. So space analysis. Right, and then you have again the swap. I'll just rewrite it here just for clarity, A and B, and then you have temp equals to A, and then A equals to B, and B equals to temp. All right, and then when you would like to analyze the space, it will say, okay, what are the variables? What kind of variables do I have? So you say, okay, I have variable A, I have variable B, and I have a variable temp. Right? Do I have any other variables? Nope. Nope. So we have 1, 2, 3. And each one of them, because algorithms usually act on the same type, right? So if you are dealing with integers, you're going to have everything is integers. If you are dealing with persons, then everything is going to be person, right? Because it deals with a single data type. Let's say most of the time, just for the sake of the argument. So this is actually going to take 1 unit of space. This will take 1 unit of space. This will take 1 unit of space. It could be 1 megabyte. It could be 1 kilobyte. It could be 1 terabyte. Nobody cares. What we care is that it will take a single unit of space, right? And then when you try to think about this, you will say, okay, so the space function is going to equal to another constant, which is 3, right? Which is actually super easy right now. Okay. Is everything is okay? Do you have any questions so far?
No, it's clear.
Okay. Let me draw a line here. Let's talk about there's one thing I would like to mention, but we're gonna revisit again, which might sound confusing. But once we revisit it again, we're gonna actually talk about this. I would like to talk about this O, when you say O of n or O n square, when you see it like everywhere on the internet, people talking about it. Unfortunately, people are mixing the difference between a asymptotic notation and a function order, and we'll talk this in detail. But I would like actually to, before I actually jump in, I would like actually to give you a small example. Let's see how you guys are going to analyze this. If we consider x equals to a times 5 plus b times 6. Can somebody tell me, let's say, the time analysis of this?
Maybe 2 units of time.
It's 3 units of time.
Can you please tell me why it is 3?
Because the first unit of time is A times 5, the second is B times 6, and the third is A5 plus B6.
Yeah, and you are missing one more.
Is it X?
Yes, assigning the result to X.
So it's 4 units.
Yes.
Yeah.
Yep. Now this is actually a 4 unit, right? So right now we see the whole picture, right? It's just a 4 unit operation. However, in algorithms, we say when we do such an analysis, whenever we find a constant, when you have a constant time, we say it takes 1. We approximate it to 1 because it's actually negligible, let's say, in the grand scheme of things. And you will see in a second why we sometimes neglect these constants. So yes, indeed, it takes 4 space units, or 4 time units. But because it's a constant, we just simply approximate it, and this is it. As I said, we are actually, in algorithmic analysis, we are approximating our analysis. We are not giving something that is by the microseconds or nanoseconds. This is the job of a profiler. So when we profile, right now we get these exact numbers. Okay.
I have a question.
Yes.
I just didn't quite understand. So basically, this is a 4 time units operation, but because these numbers are constants, we do not calculate them.
Yeah, we just consider them as one, and this is it.
All right. Okay, I understand.
Okay. Because no matter how many times you execute, this is going to be the same. That's the point of it, right? Let me see here. So whenever and this is the point about the asymptotic notations and stuff, which we're going to visit for sure. We have constants. Constant execution times, let's say. So constant execution time or constant space. Okay, so whenever you have a constant execution time, we say that the time complexity, we might say, that the time complexity is O of 1. Okay, and it reads, you read it that way, it reads, you read it, order, order of 1. This is how it reads. Order of n squared, order of log n, or order of log, or order of n log n. Okay, so we read it that way. This O stands for the order, and because it's an order, because we are talking about the order of a polynomial function. Stepen functie, if you're not familiar with the English term. So from the school, do you remember if somebody gives you like x squared plus ax plus b, what is the order of this function? Can somebody remember?
x2.
The order of the function is actually 2, right? Because of the highest number. It's a square function, right? It's a quadratic function. So that's because of the highest. Oh boy. I forgot. Somehow the name escaped me.
Exponential.
Exponent. It's called exponent. Thank you. So this is like suddenly the word escaped me for some reason. So the highest exponent in a quadratic function is actually the order of the function. So actually, if this happens to be like this, what is the order of this function?
3.
It's 3. So it's actually n cubed. So it's actually quadratic. Sorry, it's a cubic function, right? So this is the order of the function, because all of algorithms are actually running at this polynomial time. When it comes to satisfying, okay. Okay, and this is actually it. So I will actually stop right here. I just wanted to mention this because we're going to talk about asymptotic notations and categories of functions. When you see something like big O or big theta or small o or small omega, let's say, functions, these are called the categories or asymptotic notation of a function growth. We're going to talk about that later. But I'm just simply making a small intro before we jump into other topics, right? So this was actually like relatively simple, right? There's nothing fancy in here. Let's talk about the frequency method. Frequency method of calculating space or time complexity. I'm just going to write here frequency method. Now, assuming that we have a problem that does this. So it actually does, I will actually write it in the middle because I'm going to do analysis on the left and the right. So let me just try to move it a little bit here. Sum of array or A as a, array of numbers and the count of the numbers. Like you need to know how many elements in the array. So the thing goes like this: S equals to 0, and then you have a for loop from I equals to 0. I is less than n. I plus plus. Then within the for loop, we have S equals to, which is the summation, right? Close this, then we return S, and then we close. Okay, assume that you have something like this. Move it right here a bit. Okay, and you would like to calculate the time complexity of it. So let me pick up something a little bit more visible. So I'll pick up yellow. How much this will take? This one.
1.
So let's move this. So this is 1. Now let's analyze this for. This will run how many times?
1.
1. How many times will this run?
It's gonna be equal to n.
N minus 1.
Actually not. It's actually n plus 1. How many times will this run?
Also 1? Or no? No. It's not 1.
Anybody can give us a guess?
2?
Dude, it's I plus plus. Like it will run as long as there is an n, right? If this is 10,
I forgot.
Right? So this is going to be n, and this is n plus 1. Can somebody tell me why this is n plus 1?
Well, maybe because it's gonna run for the n times, and then the plus 1 for the I.
And then actually the plus 1 for the bound check, because it will actually because if you are actually having an I, if you are counting from 0 to 9, it's going to be 10 times, right? So if I is going to be, let's say 10, if you have 10 elements in here, and you are counting from 0, so I equals to 0, you will reach 9. This is right now 10, which is n, which is the same as n, right? The same as, hang on. So if n equals to 10, right? So you have 10 elements. I is counting from 0. Once you reach the 10th element in the array, the I is going to equal to 9. Am I right?
Yes.
Okay, 0 base. Now you're going to actually increment again because of the for loop. The for loop just keeps running. It will check. Is I is less than 10, right? Because you have 10 stuff in there. And it will say yes. So increment it. So once it actually increments it, sorry, it will increment it and then check it. I just mixed it up. So it will increment it and then check it. And once it sees, okay, that I is 10 is not any more less than n, then it will just simply kick out. This is why n plus 1, because of this additional increment was going to happen, right? So this will actually end up with something approximately of 2n plus 2, right? I think. Approximately, we approximate it as n plus 1. Okay, and now let's move on. How many times will this run? Can somebody give me an answer? Actually, you know what? Let me not confuse you too much. Let me actually make this as n plus 1. We approximate it to n plus 1. Can somebody tell me how long this will run? How many times will this run?
3 times.
No, it's not going to run 3 times.
4.
N times.
N times.
N
Because this
plus
is
2.
running at n. This is n times repeating, so this has to run n times, right? If this is actually 20, this will run 20 times. If this is 30, this will run 30 times, right? Are we okay with this? Are we confused?
No, it's okay.
It's fine.
And this?
Just once.
Just once. So this is actually going to be 1. If we sum this, if we take a summation of this, approximately we can say that this is going to be like n plus 3, or 2n plus 3, sorry, because there's an n, there's an n. Okay. So what is the order of this function? Right? Because of the n is actually going to be having the highest exponent here, then you're going to have actually O of n. This is actually going to be the order of the function. This is the time per complexity bit.
I have one question.
Yes.
When we calculate the order of the function, so let's say in this example, it's going to be order of n. Do we take the exponent of n, or do we just take the whole n?
No, we take the whole n.
Oh, okay.
So that's the most important thing. Now let's talk about the space, shall we? So let's analyze here. So space analysis. Now space analysis, what do we have here? We have A, which is an array. What is the size of the array?
N.
Okay, so it takes n words, right? This is the size of the array. And then we have n, which is actually assignment of a number, because this, you know, when you pass an array and you pass its size, so you assign n to 10 or 15, right? So this is actually 1. This is one space or one word. You have s, which is defined once, which is going to be one word. And then you have I, which has been defined here, which is also one word, right? So the space function is going to actually equal to n plus 3, right? So n plus 3 other words, which we call the degree or the order of the function. Order of n, or we can say it O of n. Okay? There you go. Just let me center it out. Is this clear for you guys?
Yes.
I don't understand that for loop, the time complexity of n plus 1. You change it from 2n plus 2 to n plus 1.
Approximated it. I've just approximated it, nothing more.
So you just basically eliminated the
The
e
other
equals 0.
numbers.
Okay, so you just took the checking part.
Yes, because this is actually the largest part of it. This is the most important bit of it, right?
Okay.
At the end of the day, whenever you see a for loop, you're just going to call it n. This is it, right? whenever you see a while loop and a for loop, it's going to be an n. If you have nested for loops without any if statements, let's say nested for loops, it's going to be n squared. And you're going to see that later on. It's going to be, and it's actually going to be, it's actually relatively easy to see this. It just needs a little bit of training, okay? The just like the most important bit here is these numbers are not super important. Like these numbers are not super important. These guys are not super important. What is important for us is the degree of the function, of the polynomial function, and how many n's do we have, right? Are we having an n squared? Are we have n cubed? Are we have n cubed plus n squared, or whatever you would like to call it? So are we having these crazy huge numbers or not? This is the good question. So what does it mean actually? Like before we're wrapping up, what does it mean O of n? Right. This is the question. It means that. It means first of all it's a linear time. So this is linear. Let me just write this in another color. Let's say I don't know why. So this is what we call linear time, and this one as well, linear time, linear space in this case because it's space complexity, right? So a linear time means that it will take you exactly the amount of time it needs to process. Okay, hang on. Let me word this in a bit different way. So if you have 10 elements in an array, you will process them 10 times, not less, not more, but exactly 10. The element, as much elements you're gonna actually have, the more the elements you have, the more processing power you will do. It's actually linear, right? So if you have like if you can plot this, you can say, okay, these are the number of elements. Elements or data, and this is the time. It's actually going to be linear. Okay, the more elements you have, the longer the time it gets. It does actually calculate. Okay, so this is the point. This is where we are actually measuring time. This is what means that this is what we mean by order of n. When somebody tells you that an algorithm just takes it's going to take order of n or O of n, means that it's like if you have 1 million elements, you're going to do 1 million operations, right? And when you have O of n in terms of space, it means that if you have 1 million, let's say 1 million objects, and each object is 1 megabyte, that means you're going to have 1 million megabytes of space needed in order to execute that algorithm. Okay, this is what it means when you hear somebody talking about O of n or something like that. Does this make any sense to anybody?
Yeah.
Yes, it does.
Okay.
Yes, it does.
Excuse me.
Yes.
Can we check right from there if algorithm could be less time complex?
Having a less complexity. Like
Yeah, can we check when the algorithm is big? Can we check like if the algorithm could be less time complex without rewriting it or fully analyzing it?
you actually you see like it really depends on the algorithm. Sometimes an algorithm has a branching statement, like if statement is called the branching, and you actually have to take into account the best case and the worst case, we call it. If you want to know if an algorithm, because sometimes an algorithm can behave in best cases more efficiently than others, and in worst case scenario, you can actually give it like it behaves really, really bad, right? If you would like to convert an algorithm to be more efficient, you have to rewrite it. You have to write a different algorithm to make it more efficient. So this is hopefully answers your question, if I understood you right. Does it?
But can we be sure if we can make it more optimal, or do we have to just try and check it?
No, you actually have to. First of all, if you would like to know if the algorithm is efficient or not, is to test it, right? This one actually gives you, like, for example, it gives you an idea. Let's say, for example, let's say for crazy reason, let's say that this line of code executes in 1 second for any crazy reason. But let's say, for the sake of the argument, for example, that this takes 1 second. That means that if you have 1 million items, it will take you 1 million seconds to finish this operation. Like, this function will finish in 1 million seconds. Now the question comes here is, when you actually know this, will you actually carry on and do it and test it, or will you actually, like, you know, try to make it more efficient? Right now it's actually up to you. But again, I'm pulling out this million because you, for example, have tested this in your code. You realize it's actually, like, it takes this amount of time. For example, you have a very weak computer, you cannot test 1 million, but you tested on 10 people, right? Or 10 elements. So you discovered that every element takes 1 second, and you say, aha, let me plot this. So if I have 1 million, that means I'm going to have 1 million operations, 1 million seconds. And right now you need to go back to the drawing board and make another algorithm, basically. It usually, like, this space complexities or time complexity analysis, we do it in order just to check the viability. Is it a good idea to do it or not? Let's say if I'm receiving a scientific paper, I'm looking at it. In scientific papers, people write the algorithms and write pseudocodes, and they say the complexity of it. And if I see the complexity is actually worth it, let's say it's O of n or O of log n or n log n, whatever, I will just simply say, okay, this is more efficient than the algorithm which I was using, let me implement it, right? Otherwise, I might, for example, discard it because the scientific paper says, hey, that this algorithm is actually behaving as cubic or even more, right? Maybe it's n to the power of 5 or n to the power of n. Right now, it's actually crazy numbers, right? So that algorithm, for example, is inefficient. So I don't need actually to even test it or even look at it, right? Hopefully, does this answer your question?
Yes, thank you very much.
Mm-hmm. Are there any further questions, guys? If there are none, I will actually post this on the OMS, and I will post the pages of the book. And then next class, we are actually going to continue working with time and space complexities, and maybe even focus more on the time complexity. We're going to have more and more examples, so you can see all the possible variations of pseudocodes or quote unquote program codes that you can, like, analyze it, and when you see it, you immediately know how to, you know, calculate these analysis, time analysis and space analysis. Okay. All right. Wish you guys all the best. If you have any questions, feel free to send me over the email or over MS Teams via direct chat. And if I'm there at my PC or I actually be able to answer, I will immediately answer. All right. I will actually try to stop the recording if I can.